Let's look at a point on a circle and track its position as we rotate the circle around. As the angle of the circle changes, the point moves up and down and back and forth, but its distance from the center of the circle remains the same. It's always one circle radius away from the center. If we only look at how the point is moving up and down, we see it starts at a height of 0, moves up to a maximum height of 1 radius, and then goes back down to 0. It then passes below the center point, which we could consider being a negative height. The lowest height will be 1 radius down before rising back up to 0. As we rotate the circle, the rate at which the point rises and falls doesn't remain the same. As the circle rotates up from 0 degrees, the height is growing quickly. And as it nears 90 degrees, the height is growing slower and slower. Instead of looking at the height of the point, we could consider its position side to side. We'll see a similar pattern with the point starting 1 radius to the right, coming in to meet the center at a distance of 0, then moving over 1 negative radius to the left, back to 0, and returning to the right. We can use this point to form a triangle, with the circle's radius along with its vertical and horizontal position. As the circle rotates, the shape of the triangle will change in a pattern from being flat to tall, and so on. The vertical distance is the edge of the triangle opposite the angle of our circle, and the horizontal distance is the triangle edge adjacent to the angle. These edges meet at a right angle, creating a right triangle, which makes the radius the hypotenuse of the triangle. We can look at the pattern for how these edges grow and shrink in different ways by comparing the sides of this triangle. For instance, we could see how many times the hypotenuse fits into the opposite edge. At 0 degrees rotation, the height of the opposite edge is 0, so the hypotenuse can fit in 0 times. At 30 degrees, the opposite edge is exactly half the hypotenuse. And at 90 degrees, the triangle collapses and these two edges are equal. Comparing these two sides of the triangle is called a sine relationship. If we look at the sine ratio as the circle continues to rotate, we see it oscillates up and down in a repeating wave between values of +1 and -1. The different speeds that the height is shrinking and growing gives the sine wave a smooth curving shape. We could also see how many times the hypotenuse will fit into the adjacent edge. This relationship is called a cosine. We see a similar wave like we had with the sine, but the result is offset. At 0 degrees rotation, the sine wave is at 0, while the cosine is at 1. A third comparison we can make is to see how many times the opposite edge will fit into the adjacent. In both sine and cosine, we were considering the hypotenuse, which always remains the same, so the results would oscillate between values of +1 and -1. But now, both sides are changing, so we're going to get a very different result. At 0 degrees, the triangle's collapsed, and we can't fit any of the adjacent distance into the non-existent opposite, so the ratio is 0. At 45 degrees, the two edges are the same, so the ratio is 1. As we keep rotating, we can quickly fit more and more of the shrinking adjacent into the growing vertical opposite. Until around 90 degrees, we can essentially fit an infinite number of the non-existent adjacent into the vertical opposite. The graph line shoots upwards towards infinity until just past 90 degrees, the pattern flips. The adjacent edge is now a tiny negative number, so the graph line grows upwards from negative infinity. As the adjacent edge begins to lengthen, we're able to fit in fewer of them. The ratio shrinks down until it reaches 0 again, and the pattern repeats. This relationship is called a tangent. Sine, cosine, and tangent are essentially just 3 different perspectives we can use to look at this pattern of a point rotating with a circle.